You can hear me, guys?
Yep.
I can't hear you. Give me a thumbs up if you can hear me. Okay. Thank you, Ilana. Thank you, Elisheva. Okay, welcome. Let me go back here. Funny to be in this room without you guys here. But I guess my fault, I don't know. I do remember that nobody said there's no classes, and I did think of that. But I thought, well, you guys were saying you're going to the tests, so I figured it. And then you said you went to, I don't know, somehow I thought that was overruled. Anyway, you see here I added chapter 10 and 12. Not to terrify you, but they're very short. We'll get to them. Just a few points I want you to know. I minimized them, but we're in chapter 9. Should I record? We are recording. Okay. Hello, Leora. Who is that? Oh,
this is Rahali. Say hi.
You have to send me a chat. But he's very cute, or she. I act. Okay. Where's the chat? How do I open the chat? Daughter, Racheli. Hi, Racheli. Welcome. You'll also be a computer scientist, like your mom. Okay. So here we are. Yeah, I can see your chats now easily. Virtual memory, we're on, is Zahava there? Yeah, I see, she's there. Okay. Okay, so we were in chapter, we were here. This is not going to work so well. There. We were here. We did this demand paging example. And we talked about paging, if you remember, we're up to slide 21. Oh, okay. No, we're not. We are? We did copy on right? Yeah, okay. Well, no, we don't think we are. Although we'll get there quickly, Zava. Anyway, copy entire process. So demand paging optimizations. We showed that demand paging the paging, when we miss a page, it makes us be very slow. Because it's a lot slower to get the page into memory than to use our, from disk than to use our memory. So we want to have very few page faults. So that's why they have this topic, demand paging optimizations. Copy entire process image to swap space at process load time. Then page in and out of swap space, which is faster because of how the swap space is designed. This is just saying put the process into swap space and not into, well, I don't want to skip this slide, it's not important. But cow, we did mention cow, copy on write. We mentioned that before, and what we said is that we allow the parent and child to initially share the same pages of memory. And when you spawn a child, when you do, copy on write is only relevant when you're talking about creating a child process like with fork. And maybe we did talk about this. Okay, we did talk about this. Okay. And I'm gonna actually want to, here, I'm gonna skip all of this and here. Okay, so let's start here, 23. Sorry, I just skipped a couple slides. What happens if there is no free frame? So that's an important question, right? In other words, we mentioned this. What does it mean, a frame? A frame of memory. We want to bring in a page, but we don't have a place to put it. So that's what I write in the first two bullet points here. A bad solution is to kill one process. So one solution, the worst possible solution, would be to kill one process, and that would free up memory. Another solution is to swap out a process, to entirely swap out a process. Consider a third solution, and this is obviously the one we're interested in, page replacement. Find some page in memory, but not in use at the moment, and page it out, which means copy it back to the disk. Copy the page to the swap space in the disk. So whenever you see swap space or swap, it means the swap space on the disk. Mark the frame as invalid and add to the frame free, add to the free frame list. Load a new page into the free. We kind of touched, we discussed this really. Performance. We want an algorithm which will result in a minimum number of page faults. In other words, we're going to choose which page to pop out, and we want to have some kind of performance. We want to choose a good algorithm. The same page may be brought into memory several times. I could break it out and in and out and in. It'd be nice if we would somehow know which pages in the future would be very useful, which pages will be used a lot, and then keep those ones in, and the ones that are not used, keep those ones out.
How is the third and second solution different?
If a page has not been written to while it was in memory. So, okay, so now we're talking about like this. When we take a page out, we have a page in memory and we're going to store it on the disk and delete it from memory. But what if there were, so we have two choices. Either since it was copied into memory, right? It used to be on the disk. Now we copy it yeah.
I have a
Let's
question.
assume, remember, we said in this slide over here.
He can't hear us. You have to type it in the chat.
Oh man. Okay, thanks.
Copy entire process image to swap space at process load time. So let's assume we're doing that. So that means the whole process is in disk actually. And then we're going to copy some of it onto memory. And now what's going to happen, this is going to give us a certain advantage, which is over here, that the whole process is in disk and some of it is also in memory. The part that's actually being run at the moment is going to be in memory, but the whole thing is also on disk. And it's kind of like a, it's like kind of like a backup. Once we started, let's maybe I can explain this in 3 steps. The first step is there's a program, or maybe more. There was a program on the hard drive and it's not running. We want to run the program. So we bring it into memory, we bring some of it into memory, and the rest of it we put onto the swap space as a running process though. It's not the same as the code of the program that was on disk. It's like a version, it's like a copy of the program in the swap space, of the running program. So it's the process. The process is in swap space. And then some of the process we page into memory when we need a page of that process. So now we have a situation where this is kind of like 3 copies of the program. There's the program as it was created on the hard drive. Then there's the program when it turned into a process in the swap space. And then there's some of the program in memory. Now we're going to ask the question, we're going to move some of it from memory. We need to remove some of it from memory. So we have 2 possibilities. Either there was changes in that code, or there weren't changes in that code. If there were changes, if we manipulated and changed the code that's in the actual memory, then we're going to need to copy it back to the swap space. But if we didn't change it at all, then we can just overwrite it. We can just mark it as free and let the next process write over that spell. So that's what it says here. If a page has not been written to while it was in memory, then there's no need to copy back to the disk or swap space on this. And it's essentially swap space on this. We don't need to copy back because it hasn't been written to. Now we will use a modify or dirty bit to reduce overhead of page transfers. Only modified or dirty pages are written to the disk in that swap space. Page replacement completes separate. So now that we have this page replacement, this completes our goal of separation between logical memory and physical memory. In other words, there's no real connection. Logical memory can be larger or smaller than the physical memory. We can have a large virtual memory can be provided on a small physical memory. Okay, I think this is kind of review. How is the third and second solution different? These are not different solutions. These are all the same These are all just parts of what we're talking about. We're talking about having a dirty bid. And that will tell us when we, these are not parts, this is all describing one thing. With the dirty bit will tell us if we need to copy the page. If there's been some writing done to the version of the program that's in memory, then we know, oh, it's been altered, better write it to swap space so that next time I want to use that section of memory, I'll have the correct version. I'll have the correct, correct version. This is just explaining it in steps, the concept. I think we kind of understand it. On the previous slides, the previous slides, nothing. It's just, we're just going into more detail. It's kind of repetitive, I think. So here, it is a little repetitive. Basically, find the location on the desired page on the disk. In other words, you got to find it. Find a free frame. If there is a free frame, then copy it into that free frame. If there's no free frame, use a page replacement algorithm to select a victim frame. Write the victim frame to the disk if it's dirty. If it's not dirty, you don't need to write it to the disk, and that'll save us a write. Bring the desired page into the newly free frame. Update the page table and the frame table. In other words, the free frame. It should really say free frame table. In other words, we're going to have to mark it as no longer free, and we're going to update the page table for that process. Remember, actually, some pages are not. Remember, we talked about inverted page tables, and those are not per process; those are per the whole program, the whole operating system. All the pages could be in the inverted page. So that's why it says update the page table, because it doesn't specify whether it's for the process or for the system, because it depends on what system, what method you're using. Continue the process by restarting the instruction that caused the trap. In other words, there was some instruction that caused a trap, and we needed the frame. The frame wasn't there. We're going to have to copy it in. If there isn't any place to copy it, choose a victim, write the victim to the swap space, and bring it back. Note now, potentially 2 page transfers for page faults. Increases in EAT, effective access time, is now increased because potentially we have to write the page out and write it back in. Now, right? We have to we don't just bring a page in, we have to do 2 transfers. And this is just a graphic representation of that. Here it says valid, invalid, and swap out a victim page, change to invalid, right? Because this is this guy used to be valid. Now we're going to change it to invalid. Now swap in desired space into physical memory, and this page is now going to be marked as valid. It used to be invalid. This one. This is more like an inverted page table, something like that. Okay. Well, it doesn't really matter. The point is, this used to be, F used to be I over here, and when we brought it in, now F is V. Okay. 2 types of algorithms are needed. So we need to solve, when we say 2 types of, sorry, I was looking at the chat if anyone wanted to say something. There are 2 types of algorithms that we need now. In other words, there are 2 problems that need to be solved. One is frame allocation, determines how many frames to give to each process, which is going to be less than their total needs. So we're going to have some way of determining, okay, give this process 3 frames, this process 5 frames, maybe give everybody equal amount of frames. We have to decide how many frames to give each process. And we have another problem to solve, page replacement algorithm. Which frames to replace, or in other words, choosing a victim. We want the lowest page fault rate. In other words, we'd like to pick pages to get rid of that are not going to be needed in the future. Now, we talked about this a lot earlier in the course. We talked about, keeping statistics. Here we can keep statistics on like how often a page is used, and then keep those ones that are more highly used. But we're not going to, I'm just saying theoretically we can do that. Let's see but that's not exactly what we're going to talk about right now. So we want the lowest page fault rate on both sides, on both first axis and re-axis. Okay. Evaluate algorithm by running it on a particular string of memory references. So whatever algorithm we have, we can take a string of memory references. In other words, this is saying, this is our reference string. So in other words, what we're saying is we want page 7, then we want page 0, then we want page 1, then we want, this is the reference, the order in which the pages of memory are desired. Repeated access to the same page does not cause a page fault. That should be obvious. It's or these are, in other words, if I say zeros, if I say like 3, 3, 3, 3, 3, then obviously there's no page fault there. So here's our reference string: 7, 0, 2, 1, 0, 1, 2, 0, 3. Okay. So we're going to use that if you see it over here again. So what does this say? This says the graph of page faults versus the number of frames. So theoretically, if I have more frames, if I have infinite frames, I should have very few page faults. In other words, as I get more and more frames of memory, as my memory gets larger, or as a particular process is granted more frames, either way, then the number of page faults will. Oh, you want me to join from? You want to ask me questions, not writing questions. Yeah, I could do that. Just a second. Okay. Wait. Oh, I hear myself twice. Okay. Are you hearing me twice? Are you hearing me twice? No? Okay. So everyone understands this graph? This is just saying that if obviously as I throw more pages, I'm gonna have fewer page faults as I throw more pages, as I get more pages. But wait, do I have this mention of anomaly? Where is it? It doesn't have it here. Okay. There is an anomaly. It doesn't have to be this way. That it definitely goes down. Because, well, it depends on the string of pages. It's possible that if you have fewer pages, you could have actually more page faults, depending on the access, the exact access from that list. Okay, well, let's do an example. So we're back to our first in, first out FIFO algorithm. If this is our reference string, and assume we have only 3 frames, 3 pages can be in memory at a time per process. This is horrible. I'm hearing myself.
Maybe click mute on the computer.
Oh, and then you'll only hear me by the phone.
Yeah.
All right, I could do that. Let's try that. Wait a second. Where is mute? Mute.
The phone is muted, so we can't hear you.
What was I having? Okay, now you hear me?
Yeah.
Okay, so that's good. Thank you, Gabriella. Good idea. All right, so tell me, yeah, that works better. So obviously the first page fault is going to be 7, 0, 1. Now comes along 2, and we're going to pick, who are we going to kick out? You tell me, who are we going to kick out? Remember, it's first in, first out. So who should we kick out?
7.
7. He's the first one in, so he's going to be the first one out. He's the oldest one. Notice we're getting rid of the oldest stuff. Get out with the old and in with the new. So we get rid of the 7 and comes along 2. Now we want 0. Well, 0 comes along, but 0's still there. So we don't have to do a page fault. But then 3 comes along, and we need to kick out the next oldest one. That's 0. Even though 0 has been accessed twice, we don't care. We don't care about how many accesses. We just care first in, first out. So we're going to get rid of 0 and 3 is going there. Now, again, we need 0. We didn't know. If we had known, wish we would have known, but we don't know. So now we're going to kick out 1 and put in 0. So now our current situation is 2, 3, 0. And then 4 comes along. So 4 is going to kick out 2. Then 2 is going to come along. It's going to kick out 3. 3 is going to come along. And since 3 was just kicked out, we're going to have to kick out 0 and put in 3, et cetera, et cetera, et cetera. So now you have to ask yourself, how many page faults were they? Oh, here it is, Baladi's element. That's what I was looking for. You have to ask yourself, now, how many page faults actually were there? Well, this was a page, when 7 went in, that's called a page fault, because it wasn't in memory up till then. 0, 1, that's a page fault. Now, 2 came in, that's a page fault. Of course, that page fault required 2 transfers. Well, it depends. If there's nothing dirty, then it's the same as any other page fault, even though I have to get rid of 7. Because I'm not going to transfer him back to the swap space. I'm just going to write over him with 2. So anyway, that's a page, but if we're just counting page fault, it doesn't really matter. We're just talking about how many page faults. So there was a page fault, and then 0 came, and that's the key point. There wasn't a page fault because 0 was still in memory. So not every number here is a page fault. The 3 is going to be a page fault. The next 0 will be a page fault because he's out of memory. So you have to go through this to count up how many page faults there were. Now he says, can vary by reference strings. Consider this example, 1, 2, 3, 4. So 1, 2, 3, 4. Now we're going to have to go 1, 2, 5. And then this was 1, actually, I think. So it's actually okay. 1, 2, whatever. Adding more frames can actually cause more page faults. This is called Baladi's anomaly. Let's think about why that could be. Because it could just work out that I didn't have a page fault on this 0. But if I had only had 2 pages, if I had 2 pages, if I had 4 pages, well, I still would have had it. But in certain lists, let's say here, I don't know, you can come up with a list that dafka by having more pages, you end up kicking out somebody that you actually needed. So it's not necessarily so that adding more pages, in general, it will reduce the number of page faults, but it's not not written in stone. You could work out a certain example where, because pages was longer, because I had more space, I actually got rid of a different one. In other words, when the 5th one came, let's say I had 4, and when the 5th one came and I had to get rid of somebody, I have to choose a different victim now. And dafka, because I chose that victim, I dafka needed him. And now he gets kicked out. So there's no guarantee that adding more pages in every sequence will decrease the number of page faults. It depends on the sequence. But overall, given all possible sequences, it obviously will be more beneficial. Anyway, this guy Baladi got famous for just pointing that out.
Basically, there's no fault if the number already exists in the swap space.
No, not in the swap space, in the frame. These are frames.
Oh, in the frames. Okay, yeah.
If the numbers already exist, like this 0, the key point here is to understand that this 0 is not a page fault because it was already in memory. It was still in memory at the point that I needed it. Eventually, it might come out of memory. Here, it's out of memory. In this point, it's 4, 2, 3. And then when I get 4, 2, 3, and then I need a 0, now that 0 is going to cause a page fault. I'm going to kick out the 4. How to track ages of pages? Just use a FIFO queue. Okay. Where were we? Yeah. Here's another page. Oh, I think this is just doing what we just did. Yeah, this is just doing what we did again. 7 goes in, then 0 goes in, then 1 goes in, then 2 kicks out the 7. The 0 is still there, so nothing happens. See, he has a blank space, no page fault, because this 0 was already there. 3 comes in and needs to kick out the 0, so like that. This is a nice picture. Okay, this is just the same idea. And over here you see there's a bunch of places where there's no page faults. Because when 3 came, it was in memory. When 2 came, it was in memory. When 1 came, oh, it's not in memory. I'm going to kick out the 2, etc. This is this is just showing you Baladi's anomaly, that theoretically I could have the number of pages increases, and Dafka, for a particular set of numbers, I added another frame and I actually got more page faults. Possible. The optimal algorithm: replace pages that will not be used for the longest period of time. Right? That would be the theoretical optimal algorithm. Right? If I could somehow know what will not be used in the future for the longest period of time, I'll replace him. 9 is optimal for the example in the next slide. Why not? 9? I don't know what that means. How could you possibly know this? You can't read the future. So the answer is we don't know it, but we can compare any algorithm to the optimal algorithm. In other words, if we're testing a particular algorithm and we're testing it with a particular reference string, like this one, then we can say, what would the optimal algorithm be? And let's see how many page faults we'll get. You see, that's an interesting question. Somebody with me?
I think that's what the 9 was, because in this slide there are 9 page faults.
Nine faults. Is that what it means?
Possibly. I don't know what other 9 it could be.
Yeah, that's what it means. It must be 9 page faults. So that's what it is. 1, 2, 3, 4, 5, 6, 7, 8, 9. Exactly. Thank you, Zach. So that's what the 9 was. I always thought it meant page 9. I didn't understand what they meant. But yeah, 9 is optimal. 9 page faults is the best you can do. What do I mean by that? Let's look at the optimal page replacement for the same list. What would it be? We put the 7 in, they put the 0 in, we have no choice here. In the beginning, we have no choice, 1. Now comes along 2. Well, we know that we're going to need 0 pretty soon. So we're not going to replace the 0. We're going to replace the 7. Why? Because we look forward and we see 7 isn't for way out over here. So we will replace the 7 with the 2. And now 0 comes, we don't have a page fault. But now 3 comes, we got to replace somebody. No choice. We only have our frame size. We only have 3 frames. So here's an interesting question. Will Baladi's anomaly occur in the optimal page replacement algorithm? I'll ask the question again after we finish this one. I'm just remind me to ask that question again. But it's a good question to review. So let's see. So we got rid of so which one are we going to get rid of to put the 3 in? Which is our victim? Well, if we look forward, we see that 2 is needed rather soon, and 0 is for sure needed, but 1 isn't needed all the way over here. So when we want to put the 3 in, we're going to get rid of 1. And now we have 203. Now we have 0 comes. Oh, we got it. 4 comes. So who are we going to get rid of? We look ahead and we see 2, 3 are the next ones that we're going to have. So we'll get rid of either 2 or 3. Well, 3 is worse, so we'll get rid of 3. Sorry, what did I do here? Oh, 0. 0 is worse. We're going to need 2 and 3, but 0 is the furthest away. So we'll get rid of 0 and we'll put 2, 4, 3. Now 2 is still in memory, no page fault. 3 is still in memory, no page fault. 0 gives us a page fault, and we see 4 isn't used at all, so we're going to kick 4 out. and put 0 there. Now we have 203. 3 comes along, he's in memory. 2 comes along, he's in memory. 1 comes along, we have a page fault. And we look ahead and we see 3 is no longer in need, so we're going to get rid of 3. So it'll be 201. And now 2 comes along, he's there. 0 comes along, he's there. 1 comes along, he's there. 7 finally comes along. We have to get rid of somebody. We're obviously going to choose 2 because 0 and 1 we're going to need. So we kick out the 2 and we have 701. And then the 0 is no page fault and the 1 is no page fault. So the best possible algorithm would still give us 9 page faults. Now, obviously, if we add another page here, if we'd add memory of one more page, or frame, then obviously we'd be able to fit more people in and we'd have fewer page faults for sure. So in that sense, Baladi's anomaly will not occur in the optimal algorithm. We saw the FIFO is not the optimal algorithm. There is no, we just did the optimal algorithm. It's only it requires foreknowledge. But again, it's the yardstick upon which we will measure all algorithms. So we can compare it to the optimal. So I can ask you in a question, how much worse is this compared to the optimal? Yes.
How is it keeping track of like looking ahead so far? Like, is it just when it comes to getting rid of the 7 is so far ahead, or is it just looking, okay, which two pages that are currently in the page page is still there?
Somebody want to answer? Zahava?
Is the answer that it doesn't matter because we're never using it anyway?
Kind of. I mean, the optimal algorithm does not really exist. It only exists on paper. We, as analyzers of algorithms, can talk about it, but it doesn't really exist. You can't really make a program to do that, to predict the future. Well, the best we could do is what we did before, where we had that, we kept statistics on the past and let the past be our predictor of the future. Where did we do that? And what topic was that? Somebody remember? Zava, you remember? With the alpha?
Was that with the scheduling algorithms and stuff?
Yeah.
And we did that.
Process. You see, it's all the same question. That was which process will be the next one that needs the CPU. And that was scheduling the process. So here we have the same thing. Which page will be the next one that we need? So over there, we couldn't predict the future, but we came up with an algorithm for like saying past behavior is our predictor of the future. So we could theoretically do the same thing here, but it wouldn't be the optimal. It would be a guess at the optimal. It would be an approximation of the optimal. The optimal is only something you can do with pen and paper. In other words, when you have the reference string in front of you, then you can say what would the optimal be, but you can't actually implement it in code. But when we did scheduling algorithms, we were actually talking about implementing it in code, and then we came up with like a approximation of the optimal. Now we'll do another example. Least recently used algorithm. So these are all the same ideas that we've seen with scheduling algorithms, but this is just paging, using the same basic ideas. Use past knowledge rather than future. So least recently used. So we're going to have to, actually, we're going to just mark it's a little bit different from scheduling, but we're going to just mark each frame. This we can actually do. We're going to mark each frame and give it the order that it was used. But without how we do this, let's just see. This one could be done, is what I want to say. Replace the page that has not been used in the most amount of time. Associate time of last use with each page. So you could put like next to each, like one byte in each page could be like a timestamp or something. The truth is, you don't even need to do that. You could do better than that. You could just mark it as, 1, 2, 3, and then 3 being let's say the oldest page. And then whenever a page is used, he becomes 1, and whoever was 1 becomes 2. You increment everybody. right? You decrement the one you just used. How would you actually do this? How would you know that, let's say that 701, that 7 was the oldest one? See how we put 701, and then we're going to, when 2 comes along, we're going to replace 7 because he's the least recently used. How do we know to get rid of him? Well, we just see the list and we know that 7 is the oldest, but we'd actually write here, we'd write a 1 here, then the 1 would go, then the next time we did a page fault, we would increment him, he'd become 2, and this would become 1. And then next time's a page fault, we'd increment him, he'd become 3, this would become 2, this would become 1. Now we have nobody available, so we'll choose the largest number, 3, and call him 1, and increment him to 3 and increment him to 2, or whatever, what was it? Him to, what was it? This was 1, 2, this was 1, 2, 3. So he'll become, let's say, 4, I guess. He'll become 3, and then we'll pick him next time. No, that's wrong. Well, whatever.
What did you make the 2 a 1 and then the 0, 3 and the 1 a 2?
Let me do that again. This is 1, 2, 3, right? So now we come along and see, we're going to mark him as a 3 and not change anybody. So this is, what was this? This was 3, 2, 1. So now this is, oh no, we're going to increment. This was 1. We're going to make this to a 3 and this to a 2. You're right. Sorry, I was forgetting the numbering. I should write it down. 1, 2, 3. So, no, sorry, 3, 2, 1. That's what I'm getting. This is, according to the algorithm I just told you, it's 3, 2, 1. So now we're going to get rid of 3. He'll become 1. And this was 2, so he'll become 3. This was 1, so he'll become 2. Oh, good. So now the next time, who am I going to replace? 3. He's the oldest. Well, no. This is 1, again, 1, 3, 2. So we're going to replace 0. But in this particular list, what happened? 0 got marked again. If you come to 0, that means at that moment, 0 got hit again. We're going to change this to a 1. It was a 3. This will become a 3, and this will become a 2, as far as age. So what he wrote here is that you can keep a timestamp, but another way to do it would be just incrementing everybody and then always choosing the lowest number. Or choosing the highest number, sorry. Choosing the highest number. But here, when we don't have a page fault, we still have to increment because we have to mark that 0 is the 1. Now, what happens if a 0 comes again? Well, if we 0, 0, 0, then we would leave him as 1. And we just wouldn't know if he's already 1, then we didn't change him, then we are not going to increment these guys either. Although it wouldn't really matter. We could theoretically increment them, but whenever there's a no page fault, we don't increment anybody. So anyway, 0 comes along, he goes here now. When 3 comes and needs to be replaced, who are we going to choose? The oldest. Well, the oldest is 1 because 0 is just recently used, even though he was the oldest one in the sense that he's been there a while, but it's not the oldest one, it's the least recently used. And 0 was recently used. So we're going to get rid of 1. And then comes again 0, no page fault. Comes 4, and who are we going to get rid of? 2. We just recently used 3, we recently used 0, so 2 is the one we're going to get rid of, etc., etc. So this is a nice, this seems to be a better system than first in, first out. Can somebody tell me the disadvantage of this system?
You have to keep track. You have to have some way to keep track of who was least recently used.
Right. You're going to need to either you do my system with the incrementing, or you do a timestamp, which is also going to be complicated. A timestamp means you'll have to compare the timestamps of everybody and choose the lowest one, and then choose the oldest one. It'll be more data to keep track of. You'll have to keep track of a whole timestamp. Okay. Those are, so that we saw the optimal, we saw the FIFO, and we saw the least recently used. Here he's just going to, wait, what does he say? Counter implementation. That's what I would say. Counter implementation. Every page entry has a counter. Every time a page is referenced through this entry, copy the clock into the counter. Okay, whatever. You know, you can use the clock as your counter, or you can do it my way is 1, 2, 3. When a page needs to be changed, look at the counters to find the smallest value, search through the tables. Okay, that's what we just explained. Stack implementation. Keep a stack of page numbers in a double link form. Page reference, move it to the page is referenced, then move it to the top of the stack. So in other words, you'll be moving things around in the stack. Requires 6 pointers to be changed, but you're gonna have to, if you have 3 pages, you're gonna have to move around a lot of pointers. In other words, you'll always keep, basically it's like a FIFO, but it's every time a page is referenced, we're going to have to put that page to the top of the list and put everybody else down. So we're going to move things around. And when somebody is referenced and when somebody's not there, then we're going to take away the bottom of the list, right? If we move to the top, the most recently referenced things, we keep pushing everybody else down, then whoever's on the bottom of the list will be the oldest. So each update is more expensive, but no search for replacement. I don't have, in this algorithm with a counter, you should understand that, right? I'm gonna have to check. Well, I don't know where the 1 is, or I want to find the 3 actually. So I don't know where the 3 is. It could be in the first, second, or third space. I'll have to go through all the spaces. In this implementation, I'll always push down. I'll always know that the bottom of the list, I'll have a pointer to the bottom of the list, for example. So I'll always know to get that the bottom of the list is the one I need to replace. And I'll essentially take away the bottom of the list and push the new guy to the top of the list. So this is actually a concept in all algorithms that you'll see, which is that that if I spend more time setting things up, in other words, it's more expensive to update. The more time I put into the ordering, then it'll help me later, but I've wasted time over here. Here, I spent less time in the ordering, but I have to spend the time when I want to remove it. We have this always, like in data structures, you're learning this, that the more you manipulate your data, like a red-black tree, the more you manipulate your data, the better your searches will be, but it's going to cost you more every update. You guys learned red-black trees?
Next semester.
Next semester. Oh, okay. So you're going to learn about like more complicated binary trees where, not really binary, well, it's not kind of a binary tree. And you're going to spend more energy on inserting things, but then it'll be faster to search. That's basically what's going on here between these two. Least recently used and optimal are cases of stack algorithms that don't have Baladi's anomaly. Right. That's what I was saying. You're not going to have Baladi's anomaly if you do optimal for sure. OPT is calling optimal. And also least recently used also. You're not going to have that anomaly. It's basically in the FIFO, maybe you could also do. You could also do a round robin. I mean, nobody suggests, I don't think we're going to suggest a round robin. Okay, let's go back. Use of a stack to record the most recent page references. So here, we have a new reference string. He gave us a different reference string. I don't know why, but here, 4 is at the bottom, the oldest, 7, 0, 1, 2. Well, it depends, where are we? Before, stack before A, stack after B. So, okay, fine. 2, let's see, why is it like this? Why is it like this? The most recently used is 2. The next most recently is 1. And then 0. and then you go back 7, and then 4 way back over here. So here would be our stack. And now comes along and we use 7. So 7 is the most recently used. So we push everybody down. You see all the numbers go down. And actually we slide 7 out so the 4 doesn't drop off. It would have dropped, if 7 would have been like 8, let's say, the number 8, instead of 7, then it would have been 8, 2, 1, 0, 7, because we would have just pushed everybody down. But in this case, we took out the 7 and put them over here and then pushed everybody down. So we ended up not changing the actual members. But the point is, the members of the list didn't change, but now the oldest one is still 4, actually. He's still 4. As long as he's in the list, he's going to be the oldest one. Okay. I think that should be clear. Least recently used approximation algorithms. Okay. So
Oh yeah, so I don't understand how in that stack 4, 7 jumped on top and 4 still stayed there. Surely it should be 7, 4, 2, 1, 0.
no, because 4 is the oldest one. Look, he's way over here. So he's, if I go back in this list and I say, if I'm at A, for example, and I go back, I say 2 is the most recently used, 1, and I keep going, oh, then 0, oh, then 7, and then finally 4. So now when I move 7, when after A, I use 7. So now 7 is no longer the 4th space here. He's much more recently used. So he goes up to here. But the other guys
Oh, I see what you did. Thank you.
are still, the 2 is going to still be there. The 1 will be there. The 2 I already accounted for. The 0 will be there. The 7 I already accounted for over here. So it's just going to be the 4 at the end. Yeah?
Thanks.
Okay. So in order to do this, I mean, however you're going to do this least recently used, it's going to require, all kinds of pointer arithmetic, moving things around or counters, and all this is going to be slow. So least recently used needs special hardware and it would still be slow. That's what it says here. Because remember, we don't want to take time in this algorithm. Our whole idea is to do everything as quickly as possible. Reference bit. With each page, associate a bit, initially set to 0. When the page is referenced, set the bit to 1. Replace any with reference bits equal to 0 if one exists. We don't know the order, however. So in other words, what we're saying is like this. When we put a page into memory, the idea is like this. This is an approximation of this. Let's say, let's go over here. We'll put 7 in, we'll add a little 0 over here. Then we'll put 0 over here, we'll put a 0 next to it. And then we put the 1 in, we'll also put a 0 next to it. So right now they all got zeros. Now I come along and I reference 2. So I'll just take out the first one, whichever one, doesn't matter. I'll take out a random one. But now so now this is going to have a 0 next to it, and this will have a 0 next to it, this will have a 0 next to it. But lo and behold, I reference 0. So what's going to happen to this 0? He is in there, and he's been referenced twice since he's been in there. In other words, so I'm going to change the 0 to a 1. This will still be a 0, and this will still be a 0. But this will be a 1 because I referenced him again because of this 0 over here. So now I know that sort of 0 is a more valuable number. He's been referenced twice since he's been loaded up. So now when I come along and 3 comes, I definitely won't kick out 0. I'll kick out either 2 or 1. It'll be, let's say, some kind of random choice. Because they both are 0, I'll kick them out. But the 1s I won't get rid of. So 0 will stay. Now I'll use again a 0. He'll again stay 1. He won't go to like 2 or something. Then 4 comes along. 4 will choose either 2 or 3 because they're both. So he won't do 0. He'll do either 2 or 3. Then 2 comes along. Boom. 2 will now get, let's say I got rid of 3. So 2 will get a 1. 0 will still have a 1. And 3 will, sorry, and what did I say? I forget the number. I'm not writing this, so it's hard to remember what I'm saying. What did I say? Oh, the 0 is staying here. 4 came and kicked out, so there's a 4 over here. Now 3 comes along. Which one is 3 going to get rid of? Well, 2 has been referenced twice. See, there's a 2 here and the 2 here. The 2, since he was here, when he came in, we've never kicked him out because the 0 came in. We kicked out this one, let's say. So the 3 was there. Now when the 4 came, we kicked out this one. So it's 2, 0, 4. And now the 2 comes along and boom, he gets another hit. So that means he goes up to 1. The 0 is still a 1 and the 4 is down over here. Now the 3 comes in, he's going to obviously kick out the 4 because this one's a 1, this one's a 1, this one's only a 0. Going to kick out the 4 and put a 3 there. So we're going to have, so we're going to have 2, 0, 3 like this. And then, each one, so when they're all 1, then we'll pick a random one. So what does this do? This basically gives us with 1 bit, we're only using 1 bit. Because remember, we want to keep everything small. We're using 1 bit to keep track of whether the page has been used recently, or used more than once, put it that way. Any questions on that? Wait.
What happens if they all won?
Then we'll choose one randomly. Here you see the pages, we'll choose a random. I mean, exactly how we choose it, I don't know, that could be random, yeah. Circular, we could also apply we could apply we could keep another bit to keep track of the order, well, whatever. The least recently used. We could just use a round robin. I think we would just probably use a round robin, just go down. In other words, keep track of the last one we removed and then we wouldn't keep hitting the same one. There's a danger of random is that we might keep hitting the same one. So probably a round robin or something. It's not specified. It's not part of the algorithm. You can do it any way you want. Reference bits, 0, 0, 1. Why does he say next? Wait a second. So when a page is referenced, set the bit to 1. Replace any with reference bits of 0 if 1 exists. If 1 doesn't, then obviously we'll replace a guy with a 1. We do not know the order, however, right? We don't know exactly who was most recently used. It's not least recently used. It's just whether they were used more than once. And then there's a second chance. What's the second chance algorithm? Generally a FIFO plus hardware, right? If a page to be replaced has a bit reference, if a page to be replaced has reference bit equals 0, replace it. If its reference bit is 1, then set the reference bit to 0 and leave the page in memory. Replace the next page subject to the same rules. It's a little bit different. The second chance one is a little bit different. We say like this. If the reference bit is 0 now, here we were saying if it's replace any with reference bit 0. Oh, the same thing, yeah. But here, right. If a page to be replaced, we want to get rid of a page. If its reference bit is 0, then replace it. Okay. If its reference bit is 1, then this is like it's like a modification of this. Now, this is what we said before. Here we said if it's 0, replace it, and if it's 1, leave it. But now we're saying like this: if it's 1, then don't just leave it. Set its reference bit to 0, so that it won't stay there too long. Because there's a certain problem with this one. There's a certain problem. There's a certain problem with this algorithm here. This first one. Anyone see what the problem with this? What the problem with this is? What's a potential problem with the regular reference bit that we just explained before?
Starvation.
Starvation, yeah, exactly. How would we have starvation?
If something keeps getting referenced more than once, then it will just never leave. So other pages won't get to be put in.
Right. In other words, or I'll say a case like this. It could be that a while back this page got referenced 10 times. So it's only going to be 1. Right. But if a certain page keeps getting referenced, then we'll never get him out. And there may be some other page we maybe need to get him out. So what this says is you lower him down to 0. In other words, he gets one chance to stay in memory at most, kind of. In other words, you reference him. The first time you reference him, he's 0. He comes in and he's 0. Then you reference him again, it'll go up to 1, but you have to see the example. You have to see the example here. You see, we're implementing a round robin here. I got to go to the bathroom, so just a second. Let me pause. Okay. The idea of the second chance is that you do this round robin in the next slide. Wait a second here. So you see how they drew like a circular picture here? Circular queue of pages. So we're here and we'd like our next victim to be a 0. Basically, it's like this. We're coming along here. We have our pointer here. And it says, choose the next guy with a 0. So theoretically, we would just go down, down, down and take this guy. And then these guys would stay as a 1 because they were referenced. This is the reference bits of, like, I have a theoretically here 1, 2, 3, 4, 5, 6, 7 frames of memory for this process, ignoring the ellipses here. So I have 7 frames. So I've got a pointer over here, and it says, this is your next victim. And I say, oh, but it can't be my next victim, it's a 1. So I would, in the first algorithm, I would just keep going down until I got to the 0, and that would be my next victim. So far, so good? Hello? Somebody there? Yes. Okay. But in this algorithm, we're going to do a little bit differently, because as we move down and we hit a 1, we're going to shift him, we're going to change him to a 0. Even though we access him, we're going to call him as though he's 0. So we're going to change this number to 0, like you see over here, and a 0. And then we finally do hit the 0, that'll be our victim. But in the meantime, we sort of like zeroed out these other ones that we passed over. So that what happens is next time, if I'll hit a 1. So I'll zero him out. And then I'll come to this first 0 and he'll be my first victim. So it's sort of like a combination. So this guy will be a victim, and then this guy will be a victim, and this guy will be a victim. So even though this guy got referenced, but wait a second, it could be that in the meantime, this guy got referenced. So that it'll change to a 1 again. So it could be I'll skip him. But this 1 will get zeroed out. In other words, if this guy was referenced again since the last time, then it'll go back to a 1. So it's not like automatically I'll kick this guy out. I just set him to 0 again, but if he gets referenced again, it will go back to a 1. So it's sort of, so what's the advantage of this? I mean, that's the question. What's the advantage of this than just going to this guy and choosing him? The advantage is it sort of refreshes it, and it differentiates between old references and recent references. So it adds a little bit of recentness. Because remember, in the simple idea over here, it's just whether it's referenced or not. I have no idea who's recently or who's not recent. By doing the second chance, I insert a certain aspect of recentness in, because he'll be a 0 if he wasn't recently used. Even though he was used, he wasn't recently used, he got set back to 0, but if he's recently used, he'll go back to a 1. It's a little bit confusing. So if you have a question, now it's time to ask. I think I explained it pretty well. Okay. There's another possible algorithm, a counting algorithm. Keep a counter of the number of references that have been made to each page. In other words, don't just write a 1 or 0, write 1, 2, 3, 4, 5, or 10. This one will certainly suffer from starvation, because it could be that a long time ago, I referenced this guy many times. So it's got 10, and so he never gets kicked out, even though he hasn't been used for a long time. Because everybody else I'm only referencing a few times. So this is a bad idea, really. It sounds good, keeping a counter, how many was used. But the problem is, it could be that was very not recent. Then you would have, anyway, if you would have a counter, you would have two possibilities. You'd either have least frequently used or most frequently used. Least frequently used would mean that if you have one of 10 and one of 1, you'd obviously get rid of the guy with 1. But what is most frequently used? We replace the guy with 10. This is the idea. This is here, based on the argument that if the page with the smallest count, this page with the smallest count is probably just brought into memory and is yet to be used. In other words, if this guy's got 10, then he's probably been referenced a lot. He's probably been in memory for a long time. It's probably time to get rid of him. It's kind of what you'd call in Yiddish Uberchacham. In other words, so clever that it's no longer right. But the idea of the most frequently used is to say that if you got a 10, then he's probably been there too long. He's probably no longer being used. We would not have starvation then. In this case, we wouldn't have. There's no starvation in the most frequently used. Least frequently used would have starvation. Most frequently used would not have starvation, but it could suffer from like getting rid of very useful pages. Okay. I'm going to skip that. Okay, now we're on to, remember we said there were two questions that we had to deal with? Remember we said there were two kinds of algorithms that we had to have? One is page replacement. And where was that? I forget. Whatever. We mentioned earlier in the class that there are two algorithms that we have to think about. One is choosing our victim, page replacement, and the other is how many frames do we allocate to each process? So I want to talk about that now. Yeah. Each process needs a minimum number of frames. So, for example, on an IBM 360, I have no idea what that computer is, but it needs 6 pages just to handle a move instruction. 2 pages for the from. So you're going to need a certain number of pages for each process. The maximum is the total, maximum, of course, is the total frames in the system. Right, you can't have more than the actual physical memory. So you could either give a fixed allocation, everybody gets 100, or you could do a priority. Yeah, there are many variations. Okay. That's the first one. Equal allocation would mean that if there are 100 frames and there are 5 processes, everybody gets 20 frames. Proportional would say you take the size of the process, allocate according to the size of the process. In other words, the allocation will be a function of how big the process is. Yeah. All right, I want to go on.
Can I ask a question about what you just said?
Yeah.
So 2 things. First of all, we're talking frames like in the disk, right? Like meaning if we don't have space in memory.
Say it again, we don't have space in memory?
No, we're saying like, right, if we don't have enough space in memory, so now we're like allocating frames from the disk, like as extra space, right?
No. We've gone back, that's what I was saying. We've gone back to a more basic question now. Okay, now that we've talked about how to choose victims, and we're finished with that. We have another question we have to ask, which is when I originally, in this picture, for example, each well, that's not a good example. Here, in this picture, the process has 3 frames. Who decided that? Why did the process get 3 frames? Maybe it should have 4, maybe it should have 5. So that's the question we're asking. We also have to decide the size of the memory that is allocated, and therefore the size of the number of frames that is allocated to a particular process. That's all. And it's, you know, one idea is to give everybody an equal share of the memory. Well, another idea is to say larger processes should get more. That's all. I'm not that interested in that question. Thrashing, though. Thrashing is a concept you need to understand. So let's talk about that. If a process does not have enough pages, then the page fault rate is going to be very high. In other words, in the examples that we had with these lists, where we only had 3 frames and we were constantly switching somebody out, that's not good. That's almost that. We call that thrashing. Thrashing is a process that's busy swapping pages in and out. You could have like such a thing as like complete swapping, which is like he's spending all of his time just taking pages in and paging out. And that would be, he's not getting any work done. He's just busy. The CPU is busy bringing in pages and taking out pages. For example, if the CPU itself needs to swap pages in order to swap pages, right? The CPU wants to swap pages in some process, but in order to do that, it has to run certain code. And if in order to run that code, it has to swap pages. So you could end up be in an infinite loop where you're constantly trying to bring in pages just to do the swapping, and then you have to swap out a page, and then you're lost, and so you have to bring in the page. Anyway, that's the concept of total thrashing. But in general, to give a more general definition here, is a process is busy it's busy. A process is, or the operating system is busy swapping in and out pages and can't get any real work done, can't get any of your program done. And this is because there aren't enough pages, in quotation marks. Why is in quotation marks? Because enough is a very subjective concept. The page fault rate is very high. How high is called very high? You know, we're gonna make whatever we're gonna say. If it's we talked about it being, you know, 0.000002, you know, some very small number. We want it to be, you know, thousands of times. We want, you know, 1 in 1,000 or 1 in 100,000 references to cause a page fault. If it's more than that, you can start getting to something called thrashing. So you page fault to get a new page. You replace an existing frame, but then you quickly need to replace the frame back. You need to bring it back in. So this leads to low CPU utilization. In other words, the CPU is busy doing other things. The operating system thinking that it needs to increase the degree of multi-programming. Right, the CPU is actually idle. It can actually cause, this is a bizarre thing, depending on how the operating system is written. The operating system could be written in such a way like this. Oh, the CPU is underutilized because I said the CPU is busy bringing in. Maybe I misspoke. It's not that the CPU is busy bringing in pages. Remember, the CPU it asks the MMU to go and get that page. So the CPU is idle actually, and the page is just being copied in, but we can't run the process because the process is waiting for its pages to come in. And in the meantime, the CPU is underutilized. So the operating system may say, oh, the CPU is underutilized. I better bring another process from swap, or if he swapped out a process, he may bring it back in. But that's just going to cause even more thrashing because now that process is going to want to bring pages into memory. So the CPU won't be utilized actually because we're busy copying pages, which doesn't take CPU, but does prevent any work from getting done. So this is kind of a vicious cycle of thrashing. And that's why when thrashing, you know, so what does this chart say? CPU utilization. As you add more and more programs, you use the CPU better and better, right? Because every program spends, as we said, has a CPU burst and a IO burst. So that means if you just have one process, you're for sure going to not utilize your CPU because some of the time the process is doing IO and then the CPU is idle. So you might add more and more programs. And then you get more and more CPU utilization. But at a certain point, as you add more programs, your CPU starts getting less utilized because you've added so many programs, you now have to bring in a lot of pages of memory. You're required to do more IO than you would otherwise have to do. And the more IO means less CPU, more idle CPU. So that's called thrashing. Thrashing is the moment at which you add more processes to your system and you get lower CPU utilization, even though you would have expected more CPU utilization. So now we're left with the question, why does demand paging work? After everything we've explained, it seems like it doesn't work because we're going to have all these pages coming in and out. So first of all, I'll tell you one thing, which is that the size that we allocate is nothing like this picture that we saw over here. And this picture gives the impression that that we might give 3 frames to a process, but that's absurd. We're going to give a process 200,000 frames. We're going to give them a lot of frames. So that's the first step to realize that we're going to have much less page. The more page, if we give him a lot of frames, then we're going to have a lot less page faults. In these examples in the book, we wanted to be able to show you the principle. So we had to make the frame very small, the number of frames be very small, so you'd have page faults so you can see what happens. If I had given you a 1,000 frames here, you would never have a single page fault. So the first thing to realize is that we're going to have that it's more like 100 or 1,000 or 10,000 frames to a process. The second thing is what they call here locality mode, which is, again, what's wrong with this picture. I'm sorry, I keep going back. What's wrong with this picture is that it's kind of like random. Sometimes it's 7 and it's 7 again, and then it's 4 and 3. It's like almost kind of random. But it's really, well, when you're talking about such a small number of frames, maybe it makes sense. Even this is not really random. All of these pages are less than 10. Now, they're all in the range of 0 to 10. So what happens is like this. A program, generally, when it runs, it accesses pages of memory that are nearby. Like I was telling you about going shopping. You don't shop at a supermarket on the other side of town. You shop at a supermarket near you. You go to a barber that's near you. You go to a dry cleaner that's near you. That's called locality. You stay local. So that's another reason why demand paging can work. One is that you have enough pages. You give it hundreds of pages. And another is that you have a certain locality. The process uses, even if it uses in its whole life maybe 1,000 different pages, it probably uses 50 pages and then slowly moves on to the next 50 and doesn't go back to those first 50 ever again. So we can actually ask ourselves a question. What is the locality of a certain process? And what do I mean by that question? What I mean is, what is the size of pages that it uses repeatedly before it moves on to another section? In other words, what is your locality? Your locality is your apartment to the dry cleaners, to the hairdresser, the supermarket. So it's a size of, let's say, 4. Another person's locality could be bigger because he goes to the special butcher and he goes to the special fruit store and he also goes to so his locality, in order to get something done, he needs a certain section. It's true that sometimes he moves and sometimes you move. Sometimes you move to a new location and now your locality is still the supermarket and the grocery store and the dry cleaner in that area. But your locality is, let's say, 4. Wherever, as you move, you keep needing about 4 frames. The other guy, as he moves through this program, he keeps needing about 7 frames. because he also needs a larger space. So we call that the locality. In other words, how big is the process's locality? How many pages does that process generally need? And then we can say the following thing. We'll go a couple statements. First of all, we want to give him enough pages to contain his locality. We don't give him enough. If the size of the locality is greater than the total memory of the computer, this is the sum of the size of localities. You know, if the localities of all the processes, the size of the localities of all the processes is greater than the total memory of the computer, then we're going to have thrashing. You understand that? In other words, if I need 7 pages and you need 5, but the computer only has 10, then we're going to have thrashing. If the computer has 12, we're okay. If my locality is, 7 and yours is 5, then we're okay. Even though my program in total needs much more than 7 pages, but my locality is 7. Any questions on that? Are people still there? People gone to rest and figure they're going to watch the.
We're
Is
here.
that how anyone else?
Oh yeah.
Yeah.
Okay.
Here.
What
Good.
time is this lecture ending?
What?
What time is this lecture till?
Well, we should have, I know you had an exam today, but we should have another 45 minutes, really.
Can we have a break then for maybe 10 minutes?
Want to take a break? Okay, we can take a break. Yeah.
Thank you.
And then come back with record. We're back. We're back from the break. And we're interested in this, anyway, like I said, we're now actually discussing the topic of how much to allocate to a process. How many frames to allocate to a process. So we said, we'd like to give it its locality. We first said that we could give a fixed amount, like if there's 100 frames, and there's 5 processes, give everyone 20. Then we said we could also do proportional to the size of the program. Now we discussed this idea of locality, that we said that each process has its own locality. And if we could somehow know what the locality is of every process, then we would give it its needs, its locality, the number of pages that it needs to represent its locality. So what we're going to do is monitor. I'm jumping ahead a little bit, but we'll go back here. But we're going to monitor the page references associated with that process. So for example, at time t1, we are going to look backwards in time and say, we're going to look backwards, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're going to look, let's say our delta is 10. Yeah, it's good if you turn your video on, then I can see if you're following me, you can sort of guess. 10 references here means we have 10, we're going to look backwards in time 10 references, and then we're going to count how many different pages were there. And if we look here, we're going to see that the pages were 1, 2, 5, 6, and 7, right? 1 and 1, 2, 5, 6, and 7. That means that our locality is 5 pages at time t. In other words, we needed to have 5 pages of frames associated with us, and that would be our locality. But at time t2, we're much more local. The same process. It became more local. In time t2, its locality, in the same delta we're gonna look backwards delta, and that's going to tell us that we only needed 2 pages. So we could actually give fewer pages. In other words, at time t2, essentially what's gonna happen is like this. This is called the working set model. Essentially what we're gonna do is we're gonna say at time t2, we're gonna say, oh, this process only needs 2 frames now, and we still won't have thrashing. Even though it's really looking backwards, we're gonna predict the future based on the past. So we're gonna say, now let's reduce its number of frames allocated to it to 2. And then we can have we can throw in another program. Because its history showed us in this delta time. Now in the previous slide, what we say is like this. We need to make a fixed delta. And we'll call that the working set window. For example, we'll make it 10,000 instructions. Or 10,000 page references. However, I don't know why they call it here instructions and here they call it page references. I think it's the same thing. Not page faults, page references. How many times I refer to a page? So that's maybe it's whatever, maybe not every instruction is a page reference, but it's a fixed amount of time, really. You could think of it as time or instructions, but it's the same thing because remember, instructions take a certain amount of time. So the total number of pages referenced in the most recent delta, it varies in time. Sometimes it's like we saw in the example. Sometimes it's 2 and sometimes it's 5. Here it's 5. Now, hopefully that number that we got there is the locality. But if the delta is too small, then we'll get the wrong number. We'll get us too small of a locality. Like, in other words, if our delta, if we chose our delta was only 2, then we don't look at 5 and 1 and we'd say it's only 2 pages. As we increase the size of our delta, we'll get a larger number, presumably. At a certain point, we won't get a large number. If delta would be the infinity, then it would be however many page references there are in the whole program here. In this case, it's not going to be more than 7, right? There's only 7 pages that are ever referenced in this program. So if delta would be infinity, it would be the actual number of pages we would come to would be 7. That would be our assumption that we get the locality. So 7 for sure is enough for the whole program because that's all it ever uses. If delta is infinity, it will encompass the entire program. The total demand of frames, D stands for demand. So the total demand of frames is the sum of all the working sets. If the demand is greater than memory, then we're going to get thrashing. Okay, that's not important really, but yeah, if the demand, it's logical, if the demand is greater than memory, then it's thrashing. But what are we going to do? If the demand is greater than the memory, then we're going to do what I said. We're going to swap one of the processes out or suspend a process. If the demand is very small, we might actually swap in a process. So let's do an example. Wait, does a process contain programs or the opposite? Are the terms interchangeable? Well, we're not talking about programs anymore. We're talking about processes. At this point, a program is a process. I understand your question because a program could have multiple processes in it. We're talking about processes here. If I say the word program, I just mean process. So we saw this example, but what are we doing with the question we have to ask is what are we doing with this delta? Fine, so I explained that. This delta is saying look back at this time and decide to give this 5 frames. Decide to give this 2. Now to give the process only 2 frames. So we're going to vary the size of the frames that the process can have based on its needs, its varying needs. But how are we going to know what this is? On paper, very nice. You can look at it and decide that it's 2. But how are we going to decide? So here you're going to have to help me a little bit if you can. We're going to keep track of the working set. How are we going to do that? Approximate with the interval timer and a reference bit. For example, let's say our delta is 10,000. In other words, we're looking back 10,000 references. So we'll have a timer interrupt us every 5,000 references. So in other words, we're actually going to stop at a certain point here, at time t, and count. Right? We're actually going to somehow stop and check out what our size is. We're going to have to stop. And what we're doing here is we're going to stop every 5,000 time units. So that'll be twice every window. Now we'll keep in memory 2 bits for each page. Whenever a timer interrupts, we're going to timer interrupts, copy and sets. This should be a comma somewhere here. Whenever a timer interrupts us, then we're going to copy and set the values of all the reference bit to 0. But we're going to copy, in other words, we're going to copy them right. We're going to copy. I wish I could draw on the board. I could draw here, but it's a little bit harder. Let me draw here. Sure, what here? Annotate. No. Annotate. I need to draw. Okay. So let's say we have some frame, and he's got a bit here and a bit here. And we referenced him. When we reference him, we read something from this frame. So we're going to write a 1 over here. Now, at time 5,000 units, we're going to look at all of our frames and count how many of them have a 1. You'll say, wait a second, maybe that 1 is from a long time ago. No problem. Again, we have a table of all the frames that we ever have, that we ever get all the I would say the virtual frames, all the frames, we have the frame table or the page table. And in that, we're going to have a 1 here that says we reference that page. Now you're going to say, wait a second, that could be from a long time ago. But ignoring that question for now, if I would just look at all the pages and see all the 1s, I'll know how many pages I referenced. That'll work very good for the first time that I stop at the first 5,000 seconds. That'll tell me how many pages I used in the first 5,000 seconds. Now, when I get to the second 5,000 seconds, or 5,000 time units, I'm going to copy this. Let's say I didn't reference it again. So I'm going to copy it to here and put a 0 here. Put a 0 here. So now it's still got a 1. So I still have a 1 I'm checking either one of these. Now I'll check and I'll see that I have, wait a second, am I going to count twice? That's what he means by copy and set the values of the reference bit to 0. If one of the bits in memory equals 1, then the page is in the working set. So wait, let's maybe make this bigger here. So my working set is, let's say this was a 1, this is a 1, and this is a 0. So again, my working set is going to be determined after 10,000. So after 5,000, I check, and I so far have got 2. Then I move this 1 to here, and I move this 1 to here, and I move this 0 to here. Now I check I mean, it seems like I would get double the number. I don't see why you have two bits for each page. I'm a little, yeah. Now I'm gonna have this one got referenced again. This one did not get referenced again. So this will remain, this will be a 0, this will become a 1 again. Now what does this information tell me after 10,000 seconds? It tells me that this one was referenced once, and this one was referenced twice, and this one was referenced 0 times in the past 10,000 seconds. Now, after another 5,000, after 15,000 seconds, these ones are going to get lost. But if he's still not referenced again, then this will be a 0 here, and then a 0 again here. He'll no longer be in the working set because he wasn't referenced. He was only referenced in the first 5,000, but by 15,000, he was 2 times not referenced. Question I think I'm not sure about is why it's written, why we do it twice. Here it says if we had 10 bits and interrupt every 10,000 seconds, then that would be more accurate. Why would that be more accurate? Why would that be more accurate? We'd have 10 bits. Let's say he was referenced every time. We'd have 10 times a 1 here. There are many, many 1s here. But all we care is that one time he got referenced, then he'd be in our working set. Not sure. All right, we'll talk about that on Tuesday because I'm not sure. I'll have to think about that more. Why we want multiple bits. Sorry. Let me erase that. But that's the basic idea, that we're keeping track of what actual pages have been used and based on that, we know how much to allocate. Okay, let's go on. Another method of determining how many pages to allocate to a program is by keeping track of our page fault rate, our page fault frequency. A page fault, remember, is a page that I asked for and wasn't in memory and I had to go get it from the disk. So we can sort of establish a rate that we find acceptable, an upper bound and a lower bound. Let's talk about the upper bound more. It makes more sense. Makes obvious that we need an upper bound. In other words, if it's more than a certain amount, so we establish certain acceptable page fault frequency rate and use a local rate. If actual rate is too low, is too high, then we need to give the process more frames. Process gains frames. In other words, this saying increase the number of frames if the upper bound has been exceeded. If he's got a lot of page faults, then we need to give him more frames. This is a much more direct way of determining whether we need to add more frames to this process. Simply say, keep track of how many page faults there were in a given amount of time. If it was too many, then just keep a count. If it was too many, then give him more pages. And if it's still too many, give him more pages. And if it's too low, then then decrease the number of frames. That maybe he hasn't had a page fault in a long, long time. He's probably hogging memory. Give him fewer pages. And let other people have some pages. So we sort of establish this is kind of like the way economists work things with interest rates. If there's too much unemployment, if there's too much unemployment, then they lower interest rates. They have a certain set amount, they have a goal. We want to have an unemployment of 2%. You can say, why do we want 0%? Because 0% probably means that some other problems going on. So they make a certain upper and lower bounds. And if it's beyond or either of those bounds, then we alter how many pages we give it. Okay, that's it for chapter 9. That's it. There's more slides here, but we're not going to do memory map.
One thing, we're ending here. Like, can I
was-
write that I don't have to learn past this?
So that's it. Basically, we're ending with these
They
two
can't hear us
ideas:
anymore.
page fault, just monitoring the page fault frequency, and the working set. And I need to get back to you on working set, but I want to start some of the other things that we're supposed to do. So. Noodle.
Do you say till what time we're going?
I think 5.
Okay.
Okay. This is chapter 10. We're talking about mass storage system, which is disk drives, essentially. I cut out some of the other things that I don't want to talk about. Disk drive. This is the way a disk drive looks. You know, a hard drive looks kind of like that when you look at it from outside, but inside, it's got a read-write head. It's got this little thing that can read and write. And there are sectors on platters, and there's multiple heads. So this arm extends out, and this disc spins, and it can read anything on that track of the disk. If I want to read a more outward track, then I pull in the heads. If I want to read it further out, then I extend the head. So this line here can get longer and shorter so that I can read different tracks. It's kind of like a record player, but different. You know, the famous question, how many grooves are there on an LP, on a record? You know the answer to that question? How many grooves are on an LP? It's very simple. 1. There's 1 groove. Keeps going around in a spiral, but it's 1 groove. That's not what's going on here. Here, each one is circular. In order to get to the next one, I got to get to it's not a spiral. Each one, I got to move the head. Now we call this a cylinder. You notice this, you kind of imagine a dotted line here, and you see this dotted line? This is a cylinder because if the head is in a given position, then I can read this track, but I can read this track on this disk, or on this disk, or on this disk, on multiple, and therefore we can view it as like a cylinder because I'm actually reading also the one here, and I could also read the one beneath it. If I want to read the next, let's say I want to read sector S, what do I have to do? I have to turn all 3 of these platters around till I get to where the head is. If I want to read, that's S, as long as I'm on the same track. If I want to read a different track, then I've got to do 2 things. I got to push out the head or pull in the head, and also possibly turn. But if I want to read the S and the one right beneath it, I don't have to move anything. I've got my head already at, 3 places simultaneously. I've got 3 heads, actually 6. There's a bottom one here and a bottom one here. I've got 6 reading heads. So I can read the underside of the disk also. Okay, that's the basic concept of a hard drive. Now, average access time is this minute. There's something called seek time, and there's something called like latency. We talked about this actually in the other course in architecture. But latency is like once I've actually found it, how long it takes me. I don't know why the average latency. Once I've actually found the byte, how long it takes me to read it. But then there's seek time, which is turning the disk and till I got to, and moving in and out the head. That's seek time. Okay. For example, to transfer 4 kilobyte block onto a 7,200 revolutions per minute disk, the 7,200 revolutions per minute, with a 5 milli, what is MS? MS is milliseconds, right? So that's a thousandth of a second. So a 5,000th of a second seek time on average. Why do we say on average? This is an important point, actually. Why do we say on average? Because the seek time from one sector to its adjacent sector is different from the seek time to a sector on the opposite side. Right? It takes longer to turn the disk to get to here than it does to read the next sector. So we have to talk, so we never know, any given read will have a different seek time, but there'll be an average seek time. So that's why it's given 5 milliseconds is your average seek time. And we have a 1 gigabyte per second transfer rate with a 1 millisecond controller overhead. So, you know what? I want to skip this example too. I'm sorry. I want to skip the example. I want to be able to show you better. We'll do that example again. I want to talk about this here. We'll do that example again also. So I have 2 things that I owe you. All right, now let's go to disk scheduling. So, disk scheduling is, we're back to this, really it's the same question we've been asking all along, which is we have multiple people interested in reading or writing from a disk. How do we service the queue? So we have first come, first serve. We have shortest seek time first. We have S-scan, which means, well, I'll show you an example. Let's start with here. We illustrate scheduling with a request queue, 0 to 199. So we have a request to read sector 98, a request to read, and then we want to read sector 183, etc. And the head is pointing to 53. So what should we do? Well, if it's first come, first serve, then we'll just do it in order. We'll go forward to 98, then forward to here, then all the way backward to 36, then all the way forward to 122, then backward to 14. And we'll get a picture like this, right? We're at 53. We're going forward to 98, then forward to 183, then backward to 36. We're going to keep moving back and forth. Now, these long lines here are taking time. So this is not great because we're having to go here and back and forward and back and forward. We're getting long lines. We'd like to minimize the length of these blue lines. That would minimize the time it takes. So if we took the same list, and we're at 53 again, and we do the shortest seek time first, then we select the request with the minimum seek time. So again, back to this picture. We're talking, what do I mean by seek time? We're talking by how much I have to turn the disk to get to this sector. We're all talking, we're on the same cylinder. We're talking about one cylinder and just turning it. It doesn't matter if it's on a different row or not. If it's on a different platter. But we're only talking on one cylinder. We didn't discuss anything about changing cylinders. So this is the first come, first serve. This is the shortest seek time first. The shortest seek time scheduling is a form of the, it's a form of the shortest job first scheduling. It's like when we talk about processes. May cause starvation of some requests. There might be that I have like a lot of requests around 98 and I just keep doing those guys around 53, let's say. And somebody may want to go way to the other side of the disk. I'll never get there or won't get there for a long time. So what do we do here? We do first 53. We're at 50, we're starting at 53. You have to know where you're starting from in order to do any of these. So you're starting the head at 53, and then the closest one is 65. You know, you could, it could be 14, but 14, you know, 55, the difference to 65 is only 12, so that's closer. So we go from 55 to 65, then we go to 67, then we go back to 37, then we go, now we're at 37, we're already close to 14. Now we're gonna go to 98, 122. So our total length of our blue line is shorter than in first come, first serve. So that's a better algorithm. Then we have another algorithm called scan. The disk arm starts at one end of the disk and moves towards the other end, servicing requests until it gets to the other end of the disk, where the head is reversed and starts servicing in reverse. So what this is saying is like this. We don't want, if we go back to our disk, we don't want to turn this forward and back and forward and back and forward and back. It's much faster if we just go in one direction. We'll go all the way around and then we'll come back, we'll turn it the other, then we'll go reverse it. But we won't reverse it until we got to the end. We'll have some mark, you know, we know where the beginning and the end of it is. Like some line here, one of these lines is the beginning and the end. So we'll start wherever we are, we'll go till we get to the end. Once we get to the end, we'll go back again. And we'll service whoever is there as we go. That's why it's called the elevator algorithm also, because it works like an elevator, because an elevator, as it's going up, it goes all the way to the top of the building, and as it's going up, anybody who wants to go up can get on. It opens up at any door where there's a person who needs some service until it gets to the top. Once it gets to the top, it's kind of like a Shabbos elevator. It goes all the way to the top and then all the way to the bottom again. Actually, not like a Shabbos elevator, some Shabbos, maybe there is a Shabbos elevator like that. But it goes all the way to the top. The key point here is that it goes all the way to the top. So now how are we going to view this? Notice what it goes on here. We're at 53 again, and we're going to do, we'll have to choose one direction. So we're going to go backwards. So we go first 37, then 14, and then here's a key point, it's going to go to 0. Because even though there's no request to 0, we have to go all the way back to the beginning. Because it's like the elevator that goes to the top floor or the bottom floor. As we just have a simple mechanism for how we work. We go all the way to the end, and then once we hit the end, we notice turn around and we start going back and we service them. Now this is worse than, well, is it? It's slightly, yeah, it's probably worse than the shortest. But it might be faster depending on the hardware, depending on whether it's easy to go right and left and right and left. This is better because we don't have to make turns. We don't have to start going right and left. As we go all the way to the bottom and we go all the way to the top. Now, note that if requests are uniformly dense, largest density at the other end of the disk, and those wait the longest. In other words, you could have a situation where you have a lot of requests over here for reading from the disk, and you're not going to get to them for a long time. Even though you only have one guy over here and one guy over here, you go all the way here and all the way here till you get to it. So, and it might have been faster to go to the close, it might have been over here, whatever. You can imagine that it's not going to be the best algorithm in every circumstance. This is a variation of scan. So they call it C-scan. When it reaches the other end, however, it immediately returns to the beginning of the disk without servicing any requests upon the return trip. So this one, it goes one direction, gets to the end, then fast forwards all the way to the top. This is more like a Shabbos elevator. I think a Shabbos elevator really works like that usually. Then it goes down, 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 and then all the way to the top. And then down, 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 down. So it doesn't, in here, it won't service anybody when it's going up to the top. And that's when the hardware has like a certain, it can do like an express turn. You think we're done now? Well, let's just finish a couple. I just have to finish. We're almost finished. That's the C scan. Oh, that's the C scan. Then there's the look. We'll finish in a couple minutes. Look, a version of scan. And C look is a version of C scan. What's the difference? So we have two kinds of look actually. We have C look, and look is a version of, C look is a version of C scan, and look is a version of scan. So the arm only goes as far as the last request. So it's the same as these two things. In other words, this one, we went all the way to the end. But if we do look, it's called look because we somehow have to know that there's no more requests. That's the difficulty. So we're gonna go like this. If it's C look, it's like C scan. So we're gonna go here. We're not gonna go all the way to the end. And then we're gonna go up, but not all the way to the top, just to the topmost request. And similarly, this was scan, so regular look would go forward till here and then go back to here. In other words, exactly like this, but it would go in two directions. It wouldn't just jump all the way to the back. It would service on its way up. Selecting a disk scheduling algorithm. So shortest seek, what is it? STF, shortest seek first, shortest seek time first, is the most common and has a natural appeal. Scan and SCAN perform better on systems that have heavy load on the disk. The disk scheduling algorithm should be, the disk scheduling algorithm should be written as a separate module of the operating system, allowing it to be replaced with different algorithms as necessary. In other words, you should be able to write an operating system with modules. So you have one module which does the disk scheduling, and you could change it. Either shortest seek time first or look is a reasonable choice for the default algorithm. Okay, that's all. So I owe you two topics, which is the working set and this example I want to go over. And there is chapter 12, which I'll do hopefully also. So I'll see you on Tuesday. We'll do it on Zoom from home. I'll remember to stay home. Okay. Thank you. Thank you, everybody. Bye-bye.